Picture the surface of the ocean on a perfectly calm day. From above, it looks flat, two-dimensional, a surface with length and width, but no depth that matters for the creatures that live on it. Now imagine 2 points on that surface, separated by 1,000 miles of open water. For anything constrained to move along the surface, a boat, a wave, a creature that cannot leave the water, the only path between those 2 points is along the surface itself. 1,000 miles is 1,000 miles. The distance is what it is. But what if you could fold the surface? What if you could take that flat expanse of water and bend it through the third dimension, bringing the 2 distant points toward each other until they almost touch, and then punch a tunnel through, connecting them directly? The journey that was 1,000 miles becomes a few steps. This is, in the roughest possible terms, what a wormhole is. Not a metaphor, not a science fiction device, a genuine, mathematically rigorous prediction of the theory of general relativity, a theory that has been confirmed by every experimental test we have ever subjected it to, a theory whose equations describe the actual geometry of space and time in the universe you live in. And those equations say that wormholes can exist. The question that has occupied physicists for nearly a century, the question that has moved in the last decade from the margins of theoretical physics to something very close to the center of it, is not whether wormholes are mathematically possible. They are. The question is whether they are physically real, whether the universe we live in contains them, whether the geometry of space-time has, somewhere in its vast and mostly unexplored structure, tunnels that connect distant regions in ways that bypass the ordinary constraints of distance and time. And there is a growing body of theoretical work, some of the most sophisticated physics of the last 20 years, that suggests the answer may be yes. Not as a speculation, not as a hope, as a consequence of the deepest principles of quantum mechanics and gravity that we have been able to work out. Let me take you through this carefully, because it is one of those ideas that looks simple on the surface and becomes extraordinary the further in you go. Start with Einstein. In 1915, Albert Einstein published the general theory of relativity. It was a complete reconception of what gravity is. Newton had described gravity as a force, a mysterious action at a distance, pulling objects toward each other across empty space. Einstein replaced this with something geometrically precise and philosophically radical. Gravity, he said, is not a force. It is the curvature of space-time, the 4-dimensional fabric that combines the 3 dimensions of space with time into a single geometric structure. Mass and energy curve, this fabric. Objects moving through the curved fabric follow the straightest possible paths, and those paths in curved space-time look like the parabolas and orbits and freefall trajectories that we observe. The mathematics of general relativity is encoded in what are called the Einstein field equations. 10 interlocked equations that relate the distribution of mass and energy in a region of space-time to the curvature of that space-time. They are among the most beautiful and most productive equations in the history of science. 1 year after Einstein published them, a German physicist named Karl Schwarzschild solved them exactly in a letter written from the Eastern Front of World War I, a few months before he died of an illness contracted in the trenches. His solution described the geometry of space-time around a perfectly spherical, non-rotating mass. It revealed something that made Einstein uncomfortable for the rest of his life, a point of infinite curvature, a singularity, a place where the equations break down and the geometry becomes pathological. We now call this a black hole. But Schwarzschild's solution contained something else, something that was noticed by Einstein himself and by his collaborator Nathan Rosen in 1935. When you extend the Schwarzschild geometry to its mathematical maximum, when you include all the regions of space-time that the equations describe, not just the regions immediately accessible to an observer, outside the horizon you find that the geometry has 2 sides, 2 separate regions of space-time, connected at the singularity, not a dead end, a tunnel. Einstein and Rosen called this structure a bridge. We now call it an Einstein-Rosen bridge. And it was formally and mathematically the first wormhole. But there was a problem that would take decades to fully understand and that is still not completely resolved. The Einstein-Rosen bridge in the original Schwarzschild geometry is not traversable. If you were to fall into one side of it into the black hole and try to travel through the tunnel to the other side, you would find that the bridge closes too quickly. Space-time pinches off, the tunnel collapses before any signal or any traveler can make the crossing. You would reach the singularity and be destroyed before ever emerging on the other side. A bridge that no one can cross is, for most practical purposes, a bridge in name only. This was the state of wormhole physics for decades. Mathematically real, physically useless. A curious feature of the equations that seemed to have no relevance to anything observable or reachable. Then, in 1988, something changed. Kip Thorne, one of the most distinguished relativists of the 20th century, a man who would later win the Nobel Prize for his role in the detection of gravitational waves, was approached by Carl Sagan. Sagan was writing a science fiction novel called Contact, in which a character travels interstellar distances in impossibly short times, and he wanted to know from Thorne whether there was any physically plausible mechanism for such travel. He had been using black holes, but suspected they didn't quite work. Thorne took the question seriously. He and his graduate student, Mike Morris, turned the usual approach around. Instead of starting with the space-time geometry and asking what properties it has, they started with the properties they wanted: a traversable wormhole, one that could be safely crossed by a traveler, and work backward to find what geometry would be required. They published their analysis in a paper that is now one of the most cited in the history of general relativity. The result was both promising and challenging. A traversable wormhole is possible in general relativity. The equations permit it. There exist solutions to Einstein's field equations that describe wormhole geometries, stable enough for a traveler to pass through without the tunnel collapsing. These geometries are mathematically consistent and physically well-defined, but they require something strange, something that does not obviously exist in the universe in any form we have yet detected. They require exotic matter, matter with negative energy density. In ordinary experience, energy is always positive, mass is always positive. The stuff of the universe, particles, fields, radiation, contributes positively to the energy of a region of space. But to keep a wormhole open, to prevent the throat from pinching off under its own gravity, you need matter that pushes outward rather than pulling inward. Matter with a kind of anti-gravitational effect. Matter formally with negative energy. Does such matter exist? There is a quantum mechanical effect called the Casimir effect that produces something that behaves like negative energy in a very specific and limited context. Place two parallel conducting plates very close together in a vacuum, and the quantum vacuum fluctuations between the plates are suppressed relative to the fluctuations outside, producing a tiny attractive force and a region with what functions as a negative energy density. This has been measured. It is real. But the amounts involved are minuscule. The Casimir effect produces negative energy densities so small in regions so tiny that using them to stabilize a macroscopic wormhole, one large enough to be traversable, would require engineering on a scale that makes the most ambitious technology we have ever imagined look primitive beyond description. For decades, traversable wormholes remain theoretically possible but practically inaccessible. A beautiful prediction of the equations that seem to have no path to reality. Then, in 2013, something happened that changed the entire conversation. Two physicists, Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford, published a paper with a title that looked like a simple equation but contained potentially one of the deepest insights in the history of theoretical physics. ER equals EPR. ER stands for Einstein-Rosen, the Einstein-Rosen bridge, the wormhole. EPR stands for Einstein-Podolsky-Rosen, a 1,935 paper in which Einstein, Podolsky, and Rosen described what Einstein called spooky action at a distance, what we now call quantum entanglement. The phenomenon in which two particles, once they have interacted, remain connected in a way that transcends distance. Measure the spin of one entangled particle and you instantly know the spin of its partner, regardless of how far apart they are. What Maldacena and Susskind proposed, based on deep results in string theory and quantum gravity, not as a loose analogy, but as a precise mathematical statement, is that these two phenomena are the same phenomenon. That quantum entanglement between two systems is not just analogous to a wormhole connecting them, it is a wormhole connecting them. The spooky, non-local connection that Einstein spent the last 20 years of his life trying to eliminate from physics is, according to this proposal, a geometric feature of space-time itself. The entanglement is the tunnel, ER equals EPR. If this is right, and the theoretical evidence for it has grown substantially in the decades since the paper appeared, then wormholes are not exotic structures requiring impossible engineering. They are ubiquitous features of quantum space-time arising wherever particles become entangled. The universe is threaded at the quantum level with an incomprehensible number of microscopic wormholes, each one connecting entangled particles in a web of geometric connections that underlies the fabric of space itself. Space, in this picture, is not fundamental. It emerges from quantum entanglement. The distances and separations that feel so absolute to us are not primary features of reality. They are derived from the pattern of quantum connections between the constituents of the universe. And where two systems are entangled, where the quantum connection is maximal, the geometric distance between them at the deepest level goes to zero. They are connected by a wormhole whose length measured in the appropriate way vanishes. This is the ER equals EPR proposal in its most audacious form. And it has driven a revolution in how physicists think about the relationship between quantum mechanics and space-time geometry. In 2022, physicists at the Google Quantum Computing Lab, working with theoretical physicists, including some of the authors of the original ER equals EPR framework, ran an experiment on a quantum processor that they described as a simulation of wormhole dynamics. Two small quantum systems were prepared, entangled in a specific way, and then a signal was sent through the entanglement, traveling in the language of the theoretical framework through the wormhole, connecting them. The signal arrived with correlations that matched the theoretical predictions for traversal through a holographic wormhole. The paper appeared in the journal Nature and generated both excitement and controversy. Critics pointed out that the experiment was a simulation, that the quantum processor was not itself a wormhole, and that what was demonstrated was the dynamics of a theoretical model, not the existence of an actual space-time tunnel. Supporters argued that the distinction between simulating wormhole physics and instantiating wormhole physics is in a holographic framework where space-time emerges from quantum information less clear than it appears. The debate is ongoing, but the experiment brought wormholes out of pure theory and into the laboratory in a way that would have seemed impossible a decade ago. Now, let me bring this to the place that I think matters most. The place where the physics connects to something personal. If wormholes exist, if the universe is threaded with the geometric connections that entanglement implies, then the structure of space-time is vastly more interconnected than our ordinary experience suggests. The sensation of being here, separated from things that are there, isolated in a specific location at a specific moment, is a consequence of the classical low-resolution picture of reality that our senses evolved to perceive. At the quantum level, at the level where the geometry of space-time is woven from the entanglement of its constituent degrees of freedom, that isolation is incomplete. Things that appear separate are, in a precise mathematical sense, not fully separate. And if traversable wormholes are possible, if the exotic matter or quantum mechanisms needed to stabilize them can be realized, and the constraints on travel through space-time are not what we thought, a wormhole does not merely connect two places. Because space-time is four-dimensional, and because a wormhole mouth can be moved and manipulated, can be accelerated or placed near a massive object, causing its local time to run at a different rate from its partner, a wormhole also connects two times. Kip Thorne worked this out in detail. If you have a traversable wormhole and you take one of its mouths on a journey at high speed near the speed of light, then return it to near the other mouth, the two mouths are now at different times. The moving mouth has experienced less time than the stationary one due to special relativistic time dilation. A traveler entering the mouth that is further in the future and emerging from the mouth that is further in the past has traveled backward in time. A traversable wormhole is a time machine. Thorne showed this with complete rigor. The equations permit it. General relativity, which has passed every experimental test we have subjected it to, predicts that a sufficiently advanced civilization with access to traversable wormholes could travel not just across space, but across time. Stephen Hawking responded to this with what he called the chronology protection conjecture, the proposal that the laws of physics conspire to prevent the formation of closed time-like curves, to prevent time travel, because the alternative would lead to logical paradoxes. A traveler going back in time could meet themselves, could prevent their own birth, could create causal loops that have no consistent resolution. Hawking believed the universe would not permit this. That quantum effects near the wormhole mouth would generate a runaway buildup of radiation that would destroy the wormhole at the moment it became capable of time travel. That the laws of physics have baked into them a kind of self-consistency enforcement that prevents the past from being reachable. Whether Hawking was right is not yet known. His conjecture is not proven. It is not even fully formulated in a way that makes it straightforwardly testable. The physics of wormholes near the threshold of time travel involves quantum gravity, the regime where our two best theories, quantum mechanics and general relativity, come into contact, and where we do not yet have a complete theory. But here is what I find most extraordinary, and it is not the possibility of building a wormhole, or of engineering exotic matter, or of constructing a time machine. Those possibilities, however remarkable, may be beyond any practical reach. What is extraordinary is what wormholes tell us about the nature of the universe we actually inhabit. The ER equals EPR conjecture, if correct, means that space-time is not a fixed background arena in which events occur. It is a structure that emerges from quantum relationships. The geometry of space, the distances between things, the separations that make you here and other things there is not fundamental. It is built from something deeper, from the quantum entanglement that connects every part of the universe to every other part, in a web of invisible geometric bridges that underlies the surface reality we experience. You are connected right now through quantum entanglement to particles in the early universe, to particles that will exist long after you are gone, to particles at the other end of the observable cosmos. These connections are not metaphorical. They are the actual geometric structure from which the space between you and those particles is made. In the language of ER equals EPR, the wormholes connecting entangled particles are not traversable in the ordinary sense. They cannot be used to send a signal or transport a traveler in the classical macroscopic way. The connections are real, but the tunnels are tiny, quantum, inaccessible to anything larger than the information they carry. But they are there. The universe is woven from them. Space itself is a network of quantum connections, a fabric whose threads are wormholes, whose geometry is entanglement. When you look up at the night sky and feel the immensity of the distances, the thousands of light years to the nearest star cluster, the millions of light years to the nearest galaxy, the billions of light years to the edge of the observable universe, you are looking at a structure that is, at its deepest level, not as separated as it appears. The distances are real at the level of the physics we normally operate at. But beneath them, woven into the quantum substrate from which spacetime is made, the universe is holding itself together with connections that look, in the mathematics, like tunnels through the geometry. A wormhole connecting your future to your present. That particular personal version of the idea is almost certainly not something that exists in any practical sense. The exotic matter requirements, the engineering challenges, the protection against paradox, all of these stand between the theoretical possibility and any physical realization. But the deeper version of it, the sense in which you are already connected through the quantum geometry of space-time to the full extent of the universe and all its moments, that is not a poetic gloss on the physics. It is what the physics actually says. The universe is not a collection of isolated things separated by empty space. It is a single, deeply interconnected structure whose geometry is woven from quantum relationships, whose apparent distances are a consequence of how much entanglement connects different parts, and whose deepest nature involves something that looks in the mathematical description, like tunnels threading through the fabric of what we thought was simply empty space. The wormholes are real, not as objects you could step into, but as the geometric structure of the connections that make space what it is. They are the universe's way of reminding us that separation is never quite complete, that the distances feel enormous from the inside, but the inside is not the whole story. That underneath the vast and cold and seemingly empty architecture of space and time, something smaller and stranger, more intimate is happening. The universe is more connected than it looks. It always has been.